Hello, everybody. It is Sam, the Reclaimer developer, and today we are tackling the topic of CPU hardware, specifically how to query the operating system for its architecture, like what's its cache line size and how many cores does it have. Um, and I'll be honest, this is probably my weakest uh uh I don't know, knowledge set in terms of programming, just because I am not very confident that I can teach it well. But I was talking to a friend of mine last night, and I told them this is less about me sharing my expertise more than it is just sharing my journey, my learning process. But there's a quote that's like, if you want to master something, try to teach it. And, put together your information as if you had to teach it to other people, you know. And I'm going to take a quick sippy here. My water. It's hard to move about and do things with my new programming gauntlets. So, quick side topic to procrastinate before getting into this. Um, I have come to the realization that I'm getting old, uh, in that my wrist started hurting. This one specifically. I'm left-handed, but my right hand started to hurt pretty bad like 2 weeks ago, like right around my wrist area. So but like, this is where, most of my personal and professional work, it's done right here in front of this computer, sitting in this chair. So I guess it was only a matter of time before repetitive stress injuries started to set in. So I got these wrist straps from Amazon, and they do help somewhat. They're a little bit annoying, but I mean, I don't have too many bad things to say about them. But like, so much of my a lot of my gear here, like from these glasses that I wear to, the chair that I sit in, to like how I've got my keyboard split and like mounted on my chair's armrests, uh and the wrist strap, it's like so much of this is to prevent myself from like injuring myself from like repetitive stress injuries and stuff like that. So um it's not, I guess you would say, like very laborious field or line of work, but humans were not meant to sit in this position and stare at brightly colored things and go like this for like 8 hours at a time. But we do it, 5 days a week, 8 hours a day, maybe even more. I know definitely it's more for me, just because this is what I do when I'm not working either. So anyway, oh, and let's just get this out of the way. No, I am not trying to be edgy, but yes, these are like uh like arm warmer, like fingerless things, and these are like skeleton arms, or hands rather. No, I am not trying to be edgy. No, I am not cool. I am not cool at all. I am at the point in my life where swag does not make me cooler. I make swag lame by putting it on. So it's just something else to add some padding between me and the more uncomfortable parts of this wrist strap. But anyway, now that I've procrastinated enough, let's talk about this. So there's like the two topics that I believe are like, why, or why, just why? Like, I don't know, like what are just like some scary topics, scary programming topics, uh, I haven't actually tried to write with these on yet. Programming topics. there's two in my opinion, like the two scariest, right? That is memory management and asynchronous operations, right? Async IO. That's just what we'll call it, async IO. Now, uh this one right here, it's like a non-issue for me because I've gone over like my memory management strategies until I'm blue in the face. I've made a couple videos on it at this point. Um and the code that I wrote for the Reclaimer a couple years ago is absolute hot dog water. Like it, I don't like it at all. But that's normal. It's like the code that you wrote yesterday is gonna look worse than the code you write today, and it's not gonna look as good as the code you write tomorrow. That's normal. But even as crappy as that code is, it still works, right? It's basically we take this concept of we allocate our memory up front, and we just divide it into sections that we can use later on. Basically take any L's that the operating system is going to dish out to us right off the bat, and if we succeed, then we're good. If not, we just try again until we get it right. But what we do is we avoid fragmentation and corruption issues just by having these predefined sandboxes that, in the context of It Flies By, are called arenas. And the arenas are just basically fixed size region of memory. And I've made it so that an arena is always 64K, right? I reserve like 4 gigabytes of virtual memory as soon as the program starts. Like, that's what the engine does. The first thing that the engine does is it reserves 4 gigabytes of pages, and then we commit 64K worth of pages anytime we want to do something. It's not all that revolutionary of a it's not something that is really new. It's just something that I do, and I don't ever worry about memory corruption issues ever. I don't use smart pointers. I don't use new, malloc, free. I don't use any of that. Like, basically, there's all of these problems, or rather, we invent problems to solve that don't need to exist, right? So we've got things like garbage collectors and smart pointers and all of this other stuff to account for, let's just be honest, bad programming, right? So if you have a stack of memory and that's like fixed, I know how big it is, and I just keep track of my allocations, and it's like, okay, I want to maybe I don't know how much of something, or I want to be able to like reuse stuff. I just chop a memory region up into blocks and just reserve and release them when I need them. And that's fine. That works. And if a program is really small, like if it's really not doing all that much, just reserve some stack memory, just make a buffer of bytes, and you're done. Right? Just keep track of it, and, you don't even need to call free or delete on anything. You just terminate the program, and it's done. And, similar with virtual memory pages, because everything's done through the operating system, modern-day Windows, whenever the handle for a process is shutting down, it basically finds all the handles that are associated with it and cleans them up. So but all of this crap that we've invented, where it's like, okay, we stopped reasoning about, like, how many things, like, I don't know how many things I want to put in this list, right? That may be true that you don't know at the time, but you could, with about, I don't know, a minute's worth of reasoning be like, okay, what is the absolute maximum? What's the minimum? And like, what's the average? Right? You can come up with just some rough numbers of stuff that you would never expect to ever hit, allocate that much in a pool, and you're done. That's it, you know? But the new answer is, because we don't know how much space we want to put in there, we are just going to just have these constant allocation parades where every time we allocate something, we switch into kernel mode, and then there's a potential that the operating system could say, I can't give you this right now. It's another failure point, and it's something that needs to be cleaned up. Because the more you use the heap, the less efficient it gets over time. So, like, memory management is just a non-issue for me at this point. I'm hoping that async IO will eventually get to that point, because it just kind of makes me go like this right now. But as you can tell by the start of this note, we are specifically talking about CPU caches and CPU cores in terms of asynchronous stuff and parallel processing. So we've talked a lot about memory management. So let's actually talk about how to squeeze as much optimization out of the CPU as we can, or at least get us started thinking about these things. So, and that got me thinking to while I was thinking about how to talk about this, it got me thinking about an interview question I had a few years ago. And it wasn't a programming problem, it was a thought problem. So basically, let's sit down and talk about how you would solve this problem, right? And it's called the parking lot from hell, right? And let's just do this. From hell. Right. Which one is my gold yellow? Blah. Right. And let me go ahead and where's my drawing tools? I want to draw a square. Draw shape. And let's do this. Go away, I don't want to talk. Whoever that was on my phone. I should mute this. There we go. Do not disturb. But let's add a square, right? Looks like that. Or you know what? Let's make it a rectangle. Screw it. All right. And I'm just gonna copy this in case I want to put another one there. Copy. Right. So here's the parking lot from hell. Essentially, you have a imagine you're in hell, and you are constantly stuck in a parking lot that, you know, picture like a large concert, like a festival or a concert or something just ended. Every single person from the venue gets to their cars, starts them, and tries to leave at exactly the same time. And here is a little, like, preview of what this looks like, right? So we've got these lanes, and these are where the cars are coming from, right? I should probably use a different color for the arrows, but let me go ahead and just set these lanes up. Okay, and make that a little bit wider. And we'll just use this color to say, like, this is where the cars are coming from. They're coming in this direction, right? And so there are 2 exits out of the venue. At least that's just where we're starting, right? And so we've got an exit up here and an exit down here, right? You just say this is an exit, and this is an exit, right? So, And what makes this the parking lot from hell is these are infinitely long, right? So we need, like, our purpose here is being the conductor, right? Or, like, we are directing traffic. So we're here. We're the poor bastard that, is stuck there trying to direct everybody out, right? And what we want to do, basically, is, minimize idle time, and just basically keep the flow, keep traffic always flowing. Now, you have nothing available to you except you are stuck there, and you are just basically, you may have, like, the little wand things. I'll, like, put them on, like, here I've got, like, these little things. Maybe I've got, like, a little vest on or something. And so you're just basically directing people out. So how do you want to do it, right? So you could basically zip merge them to go, like, this lane goes here, and then this goes here. But you could also do other stuff, like, what if all of a sudden this exit closed, right? Or both exits closed, and another one opened up, like, over here, right? So the problem changes, like, as you are trying to direct things. Like, they will, exits will open, exits will close. We may have traffic flowing from different directions. Maybe you've got direction, like, the lanes are coming this way and then that way. Like, it changes all over the place, right? And so you have to adapt. But the problem is, like this over here is the stuff you need to be thinking about. Now, if you are stuck in traffic, there's a huge difference between being stuck, like, in traffic that's just, like, inching along, like, you move a foot and then stop, you move a foot and then stop, you move a foot and then stop. Like, it's infuriating. Versus, like, even if traffic is slow but you were still just constantly moving, even if you're moving at, like, I don't know, what's a slow speed, like 5 feet per second or something like that, I don't know, or a foot per second, something really slow, dog shit slow, but you're just still staying constant, that's a whole nother ball game than, like, if it's just stop, wait, inch forward, stop, wait, inch forward. And so that's what we're trying to do, is come up with an algorithm that, like, let's assume that this is just the traffic is just infinite. Like, even when the cars go out, they just automatically, like, spawn back in. They enter a black hole, and, Satan puts them back in another line somewhere, right? So you just always want to keep things moving and minimize the amount of time that people spend waiting. Well, we are going to take the parking lot from hell and turn that into a real problem that we will actually be facing in It Flies By. So here's an example, right? I have a vector. And in this context, it just is an F. It has two components, or two properties. It has basically a float X and a float Y, right? Simple enough. And what I want to do is calculate magnitude. I'm just going to say magnitude for short. and I am blanking, but let me just make sure I understand what it is. 2D, let's see, 2D vector magnitude. I'm still getting used to these gauntlets. It is square root of the sum of the squares of its components, right? Yeah, that's the magnitude. So, let's assume that the vector doesn't have a scalar. We're just going to say it has these two components, right? These two properties. So the magnitude is going to be x squared plus y squared, and take the square root of that. That's the magnitude, right? That's what I want to calculate. So here's the problem. I have infinite vectors, right? We're just going to assume infinite vectors. But here's the goal. Minimize time spent per vector. Okay. At first, this doesn't seem like too much of a task, right? So, if you've taken high school algebra, more than likely you've seen this equation before in one way or another. A magnitude is a positive value, as in, like, it's just measuring a distance from zero, and the vector components tell you which direction it's going in, right? This is a very easy problem. And so here's the... Oops. So the question is, how? Right? So, when we learn how to program, most of us, at least modern day, what we do is we think about how we would solve this in real life. So we bring in sort of like world modeling principles. So if I had a homework problem, I'm just going to say just homework, and I had like 10 problems. It was like, do 10 vector magnitude mag calculations, right? It would just be like 1, 2, 3, etc., up to 10. So how we would go about doing our homework problem is we would do the first one, and then we would do the second one, and then the third one, all the way up to the 10th one, right? Simple enough. So we pictured these vectors as, like, being one at a time. So, and we've talked about sort of this concept of, like, when we do that, we tend to, two things, right? I'm going to say world modeling. Right? So, instance thinking. Which is another way of saying one thing at a time. Right? So it's basically, I have this instance of a thing. I have an instance of a class. The class tells me the properties of the data, and like there's functions that can do stuff on that data, and I have an instance of it, and I process it, and then it may be in a collection, like a vector, or a list, or a queue, or something like that. It's sort of like in its collection, I get, you know, an instance of it, I process it, and I move on. Sort of like the homework problem. I can't do all of these calculations at once. So I'm going to just process them one at a time. I'm going to do the first problem, the second problem. I could even skip like problem number 3 if it's too difficult, do the rest, and then come back. I think we've all done that. We've done it like, well, I know I've certainly done it. Like, you skip a problem that's too difficult on a homework assignment or a test, and you're like, this one's taking too much time. I'm going to come back to it, right? So it's something we've all done. And so we've talked about, I'm not going to go through the principle again, but RAII, resource acquisition is initialization, where basically, we have, a class new, it is initial, the constructor of a class is called when we call new, and then that class has some, things that it calls new on, new, and then each one of these new, has things that it would want to do, and I'm not going to, repeat the whole tree, but you get it. And where the problem comes in is, deleting. Right? Because you have to walk this entire tree back. It's just a mess. We don't want to do that. So, let's see. I'm trying to think of the best way to frame this, because Casey Muratori did a fantastic talk. I don't know if I guess he was giving a lecture or something, but it was called N+1 thinking, where it's not, you have a thing that you're dealing with right now, but you also want to structure your data in such a way that you are also cognizant of what is the most likely thing you're going to be doing next. As in, the thing I'm doing right now is another instance, the operation I'm doing is one I just did, and I'm going to be doing the same operation again, right? So, that's going to be the most common case for doing, large amount of transforms. So, let's talk about this world modeling principle, right? So, I have a class, and I'm not picking on, classes in general. I don't use classes when I program in C++, but that's just me. I don't find them necessary. But this would be on any homework assignment, right? You have a class vector, let's just say 2D, and it has some private properties. It has private float x and private float y, and then a public method for calculating the magnitude. And it would basically, you could just say f float and just say magnitude. Right? So, and what you would, probably a common case that you would see is these are going to be in a list. Or, it's going to be a member of something like, let's see, I have a class character. And one of its properties is going to be a position, right? And it's just going to be vector 2D. I'm just going to abbreviate. And it's going to be position, right? Position. And, I guess in this world, these are sprites. And you may have other properties that are inside this. And you also have, class enemy. Or we can just say class NPC. You know what? We're just going to call this class player to differentiate between them. Class NPC. And it's also going to have a vector 2D in there as well. And so you have these, a player and an NPC are going to be initialized completely differently. one function is going to new up the character or player character. Another function is going to new up the NPC. And inside the constructor, they're most likely going to new up a vector. And there's going to be things that go through a list of players and a list of NPCs. And, the vector may be encapsulated multiple layers deep, like class within class within class and things like that. But let's just assume for a second that we don't do that, and we're just sticking to a basic list of vector 2D, right? And we just say vec 2D list, right? So this is our list. So what we would do is something like, for each, and we'll just say, like, auto vec2 in, vec2D list would be doing something like this. Magnitude is going to be like vec2 magnitude, right? It's a pretty straightforward function. Like, and maybe we are doing like some other things in here, like there's a reason we needed to calculate the magnitude, but like in this scenario, the job was to just put a collection of vectors together and calculate the magnitude, right? So we know that is going to take a certain amount of time, but we have no frame of reference. Like, let's say we have like, we're calculating the time, and we say like average time is going to be some number, right? Let's just assume for a second that we're going to make a couple assumptions. This right here is infinitely long, and this right here, we don't know what it is. We know it's going to be some number, but, if we couldn't do better, this is where the video would end. I'm already 30 minutes into this jargon. So I do appreciate everyone bearing with me here. Let me take another awkward sip of my water. I'm just going to leave the lid off. But if this is not an uncommon thing that you would see scattered throughout code, right? If you had, like, if you were in the business world and you had a list of, like, I don't know, bank transactions or, report, like if you were calculating grade point averages of like university students, you would see something like this, like just scattered into code, right? I have a collection of things, of these objects, and I'm gonna loop through each one, and I'm gonna do some operation on it. This is a pretty small function. I can read it, but this right here, can we do better? We don't even know what the number is, but can we do better? I think we can. But it's like, this is where, like, most universities and programming curriculums just kind of stop, right? They say, you got the job done, you're calculating the magnitude, you've gone through the list, don't worry about it, it's good enough. Fuck it, we're pushing it live, and there could be any number of reasons, right? Because, and like, that's what a lot of engineering and programming curriculums do nowadays, is like, get the job done. We're looking for good enough. Can we hit the deadline? I was watching a video today that the Primogen did, and I think it was done actually a while back, but it talked about, nobody cares about good quality code, okay? And it was because, like, if you are working at a company that does software, your manager is looking to Like, you got salespeople who are, trying to make a deal and, trying to, convince clients, hey, buy our stuff. And you got a manager who is trying to make sure all the stuff in a sprint gets done. You've got an executive who wants to constantly save money and replace people with AI. You've got quality assurance whose only job is to, pray to God that he smites you. And then HR wants to fire you. And, like, you have all of these different concerns that are going on. And you're, like, the only person who's worried about code quality, right? That's normal. But what the video was talking about was, like, we still have a responsibility for good code. But, like, this, like, good enough? Sure, it works. But let's go deeper, right? But to go any deeper, this is going to require us to think about the CPU hardware. Right? So, let's say, for example, I'm talking to Mr. CPU, right? And I say, Mr. CPU, I have these things I need to process. And I need to process them fast. I want to structure this function in such a way that, the time, I want to minimize the time spent doing the calculation between each instance, right? And so Mr. CPU says, okay, Mr. Programmer, you have two options for speeding things up. And both are valid, right? One, use less, or rather, let me rephrase that. Use fewer and less expensive instructions, right? And two, do things in parallel. Right? So these are pretty self-explanatory, right? So if I have a thing that I need to do, if I'm listing out instructions and I have to do things step by step, like, remember, CPUs are not magic. They are instruction processors. And, in fact, let me just go ahead and do this, right? So, we said we're going to have to talk about CPU hardware, so let's talk about it. We have CPU, right? And so here's what we got. A CPU takes in data, and it takes in, or rather, let's say, you know what? It takes in data A, and it takes in instructions. And it spits out data B. This is fundamentally what a CPU does. And it's a gross oversimplification. CPUs are extremely complex machines, at least in terms of the ones that we use in modern computers, the one that I have in this desktop, the one that you have in the device that you're watching this video on right now. But fundamentally, this is what it does. It's not magic. It takes data and instructions, and it transforms that data into other data. And a program is code just solves data transformation problems. That's all it does. Quote Mike Acton CppCon 2014. Best talk on programming ever. So, let's talk about instructions. Let's say not all instructions are created equal. Okay? So, depending on what architecture you have, there's going to be a set of instructions. Like, all instructions cost a certain amount of time, right? So they take time to execute. And the straightforward one is just like, make sure you're using the right instructions for the job, right? Do things very step by step. Don't recall, like, if you have a result of a function and you're going to need that value multiple times, don't call that function every single time you need it. Cache that value as like a constant or something, and then just pass it around to people who need it, right? So I've done the work to set it up, and I don't want to just throw it away just to have to put it back into memory later. And here's another example. So, not just that, but think about, operations, like the order of magnitude that it takes them to do something. For instance, when we're talking about arithmetic, like, we've got add, subtract, we got multiply, and we got divide, right? The first three are very simple. They could be in the ballpark of, like, no matter what, like 5 cycles or less. Maybe more. More, like, even faster than that. But this bastard down here could be, 10 cycles or greater. And I can't explain why, I just know that it is, right? And you can reason about this too. Like, think back when you were in elementary school or whenever it was that you were doing arithmetic and you learned how to divide. Like, division at the time was extremely complex. By the time you were learning how to divide, you knew how to add, subtract, and multiply. Adding and subtracting, those are mostly straightforward. I have these 2 things, I put them together, and I have a bigger thing. Or I have a big thing, and I take something away, and I have a smaller thing. And you can rewrite multiplication as just a series of additions, right? It's like 2 times 5 is just adding 2 together 5 times, right? Easy. Division, on the other hand, is a bit more complicated. So here's an example of using fewer instructions, right? Let's say I had to normalize colors, right? Normalization basically means I want to take the magnitude of something and, like, whatever the value of something divided by the, what's the maximum volume, maximum of what it could possibly be, right? So if I wanted to normalize a color, so I've got R, G, B, A, and each one represents a byte, so they are all, we'll just say 255, right? 255 bits, aka 1 byte, right? OpenGL takes in floats for colors, right? And so a use case for normalizing colors would be like OpenGL. I want to create like the float representation of a pixel, right? So what I would do to normalize that is I just say whatever the R value is over 255, and the green over 255, and the B over 255, and the A over 255, right? I do not know if a CPU at certain optimization levels is capable of finding the pattern here. But rather than do that, because what you're essentially doing is say, do this division 4 times. So that would be like, 10 cycles plus 10 cycles plus 10 cycles plus 10 cycles. and it would just be like 40 cycles of work, right? That's crazy. Or rather, it's only crazy when you realize the alternative, or rather, when you try to think about how much time you can save. So instead, just do this once on startup and store it as a constant. And I'll just call this like normal color, right? And so instead, just do RGBA times normal, da 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 da. And so now what we've done is we just say, okay, we've taken a hit for doing the division. That's like 10 cycles or something. And we do the multiply, and each one of these are going to be like 3 cycles, 3 cycles, 3 cycles. And you add these together, 3, 6, 9, 12. We've all seen Schoolhouse Rock. 3, 6, 9, 12, 15, 18. So, 3, 6, 9, 12. And so that comes out to a total of 22 cycles. So just by doing that, we've cut the time it takes to, actually, let's say if we do this on startup, we just take the hit for 12 cycles, right? Because we've already done that math. We've pre-calculated the division. We've stored it in a constant somewhere a global constant that we can just pull out whenever we need it. We may take a cache miss for like loading it into memory or something, but even still, we have basically reduced the work it takes to normalize 1 pixel from 40 cycles to 12 cycles. So what? What if I have a megabyte worth of pixels to normalize? Right? This adds up, is the thing that I'm getting at. And, but this, I've kind of gone on a tangent here, where we are talking about, how to shave off some time here and there. And I think everybody gets the idea with that. Why can I not? I do not know why I can't, do all of that, right? Because I like my CPU drawing. Can I please select? I don't know why I can't select. This is so dumb. Okay. So I wanted to do a talk on optimization strategies, like with CPU hardware, and instead this is what I'm doing, because yay OneNote. Right? We can delete that. I want to delete it. Okay, we gotta do this, and then we gotta do that. Okay, we are back. So, this is the overall hardware that we're talking about, right? But let's go a little bit deeper than that. This is just going to be the theme. We're going to keep going deeper and deeper and deeper until we get something practical we can actually use. And so to think about this, there's hardware that we can use to our advantage. And so to use less expensive instructions and to basically shave off CPU cycles, we need to think about the cache. And to do things in parallel, we're going to be talking about cores. Now, let's talk about these for a second. So, a CPU reads data from memory through things called cache lines. And we have conveniently put the two types of caches here that we have, right? And so they are conveniently called Dcache and iCache. Creatively. $$ and $I$, Dcache, iCache. Love it. And so what this looks like is it's going to be some small number. And I've already done the work on my system to figure out what it is. You could Google it, like, depending on, like, you could actually look up, the specs on the chip. You can pull it up through system information on your desktop, but what we're going to be doing is retrieving it dynamically later. So we've got this. Okay, I suck at this. Let's go ahead and put in a shape. We've got the Dcache, and we've got the iCache. Right? These aren't equal, but I don't really care. Alright. And so, this is gonna be, it's just a buffer. Same with the one below. It's just a buffer. And these are both basically 64 bytes. Right? That's how big a cache line is. So why am I talking about this? We've talked about, okay, it takes some time to do the math. Like, we talked about, like, division is more expensive and square root is going to be more expensive than division. So what? Well, here's the problem. RAM is some distance away. And let's go ahead and grab this. I hate you, OneNote. Where is, like, the... Okay, whatever. Alright, so we're gonna painstakingly slow grab all of this. I have got to optimize this later, like, figure out what to do. Oh my god. I'm just gonna be raging at OneNote, everybody. So this is gonna be, what Sam talks about for probably the next half hour. It's just OneNote being OneNote. And so we've got RAM, right? Random access memory. So I would hope everybody knows what RAM is. It is primary storage on your machine. It is, what the CPU loads all of its stuff that it's doing whenever it needs to work on stuff, right? So it's dynamic, and they are just these kind of big chips that are these long sticks that kind of look like, they're in the shape of gum sticks, and they just kind of ka-chunk into the motherboard. And, common, sizes, 4 gigabytes, 8 gigs, 1632. I think this one has 16 gigs just because I kind of put it together cheaply and didn't really think about it. So, and there's also this little device called Northbridge. Right? And this exists, I think, on the motherboard. Let me see. We want to know, like, where is the Northbridge? Where is Northbridge on computer? Is it on the motherboard? Yes, it is on the motherboard. It's near the CPU and the memory. So, yes, it bridges the gap between RAM and the CPU. So, this right here is all the CPU. All of this. So, basically, let's make a distinction here. This is motherboard. And this is, like, I'm gonna call it CPU chip. So, The north bridge is the conductor, the bridge that actually controls access from CPU to RAM. And so if we were to do the math, and remember, we saw that division was a kind of expensive operation. Square root is going to be in the magnitude of like 50, so a bit more. But this strip right here, you're going to have this boundary right here is in the magnitude of 200 cycles to bridge that gap. So there are multiple levels in which a CPU accesses memory. So let's talk about cache levels. Right? So we've got L1. We're going to say we got register. We got L1, L2, and then RAM, right? So, reading from a register, the register is essentially, it is the thing that the CPU will read from whenever it wants to do an operation. There's already data stored there, and it's essentially free. Of course, it takes time. Nothing is instant, but within the context of how fast a CPU is, it's the closest cycle is about 1, probably less than that. It's basically free. So L1 access, and these are approximations, right? It depends on the architecture. It's going to be about 3 cycles. L2 is going to be about 30, and main RAM could be 300 or more. It's an extremely expensive round trip. But here's the thing. It's unavoidable. This cache line is only 64 bytes wide. And the CPU has multiple cache lines that we can use. But every time we need to access something that is not in the cache, so basically, remember, this is the boundary. So we have between, this is memory, and this is cache. And we could also say, on the CPU, there's registers. Just to, sort of continue to put this into context, right? So every time you dereference a pointer, and the data for that pointer is not in the cache, it has to make this incredibly expensive trip to main RAM. And that is where, by far, most performance bottlenecks exist today. Right? So, the point is not to avoid cache misses. Like this right here, making this trip is called a cache miss. They are inevitable, right? You're going to have to load the cache with data as you go through it. But it's not to avoid it. It's not to avoid the cache, it's to make the trip worth it. Right? So, given that it's expensive, that's what we want to do. We want to make the trip worth the time. That's the objective here. To make the trip worth the time. And that also goes for the instructions as well. So, the instruction cache is literally what it sounds like. It is data loaded from the text region of an executable, and it goes straight to the CPU as instructions. Like, these are the instructions I want you to execute. So, let's think about cache utilization in 2 ways, right? So, we are continuing to subdivide, like, two cache methods, right? we have, so one is large array, small instructions, or large array, small function. And the other is exactly the opposite. Small structure, small struct, large function. Right? So, this one is basically same thing, lots of operations, right? Or lots, or no, that's the opposite rather. So we've got lots of stuff, lots of the same thing. So basically, we have an array of stuff, right? We pack it into the cache, and we're doing a small function. Like, basically, we keep the instructions we have loaded into the cache as much as we possibly can. We want to keep it as small and concise as possible. But we've got a very large collection of data that we're iterating through. And this one, this one would be like, i.e., vector math, right? And so this one down here would be, we have small struct, lots of instructions, or lots of instructions. And this, an example of that would be like window initialization, like a graphics window. I'm just going to abbreviate that. So an example would be like, I've got a window that I want to open, and there's going to be like, I could pack a single instance of a window, like whatever my struct is for a window, into a cache line. Like, it would be less than 64 bytes. But it's going to have some flags that say, is it open? Is it, showing? Like, what are the dimensions? What's the position? Where's the mouse? And, things like that. And, like, maybe the handle that the operating system uses to, send events to it and shit. So, like, it's going to be a relatively small struct, but it's going to be passed around to, like, a bunch of different, like, functions, or maybe, like, one big-ass function with a lot of instructions, and it's just, we're going to basically keep reloading instructions to use on the same data, or we're going to be loading data to churn through the same instructions. One or the other. Rather, try to think of things in this way. So, let's take a quick break and actually finally look at some code, okay? So, and here is a build of It Flies By. I'm going to go ahead and just do a fresh rebuild. Hopefully nothing's broken. But you can actually query this from the operating system. So, okay, looks like everything's building. And let's go ahead and look at Win32 system, right? I'm doing a bunch of stuff here, but the important one is going to be this logical processor information, right? So we're going to get to CPU cores in a moment, but each CPU core has, like, it's basically going to be the same throughout each core. 64-byte cache line, you're going to find that everywhere. So what we do here is basically get system info is going to have some stuff in it that I've already gone over, like page size, allocation granularity, and it also has something called number of processors. So this is logical processing units. I'm sort of getting into the weeds here by I'm jumping ahead of myself, but this is essentially, like, when I say a CPU core, I mean a logical core that I can actually do work on. I can isolate it. I can run threads on it, right? So, but what I do here is I want to calculate physical and logical cores, which we'll go into the difference in a moment. But how Windows likes to do this is really fucking weird. But basically, I put a buffer of information together, and I query Windows, and I say, give me information about all the cores on this system. And so I want to look up the processor core, and I say, okay, whenever you query logical processor information, depending on which flags you passed into the query, up here, like get logical processor information. I want to get everything. So I basically have to put together a buffer together, and I say, give me all of the stuff that you can, right? And so I basically advance through this buffer of information, and I look at the flag of, like, what property am I looking at? And I say, I am looking at the processor core, and an instance of that is like a physical core. It is a physical die on the chip. And so we've hit a physical core. But a physical core can be divided into logical cores, where it is a physical core, but it's emulating two virtual cores, right? So, and what this is there's a mask in there that says how many logical cores are on there. And so I just add that up, and now I can say I've got, this machine has 6 physical cores, 12 logical cores, right? So that means it's virtualized 12 cores, essentially. Oh, man, I'm just all over the place. Now, we've also got this information right here. So I want to know the cache information. And so what I do is I look up the cache level, and most processors today are going to have 3 caches, right? At least when Mike Acton did his talk in 2014, L3 caches were not as common. It was mostly L1 and L2. But this one does have 3 levels of cache on it. So 1, 2, and 3. So my diagram has another level to it, and it's probably even more expensive, I would assume, because now the cache is even bigger. So what that means is the time it takes to load that cache gets even greater. So that's what I would assume. That's what that means. I could be wrong. This is stuff I'm learning, not like it's my expertise, rather. But basically, we have a line size and a cache size. So what I'm going to do is I'm going to set a breakpoint right here. Let's jump over to Rad Debugger. And we are going to bring up the system, Win32 system. I don't know why it keeps defaulting there. I need to fix that. I love Rad Debugger, but there's just every now and then just a little thing that just kind of irritates me. Win32 source system. Okay. So we are going to set a breakpoint here, and we are going to launch. All right. So let's look at the system info struct that we have so painstakingly requested from Windows. So this is stuff that we've done before. We've talked about the page size and allocation granularity, but this is the processor information. So we can query things like what is the theoretical speed of this processor? And it's 3.2 gigahertz. It's not a pushover, but it's not top of the line either. But I would really like to get another gigahertz out of there. But we've got 12 logical processors, 6 physical, just like we talked about. And here's where I am getting a little confused, and like this, I'm getting into the territory of like, how do we properly use this, right? So we can see our cache line and how big each level is. You see each level goes up, and it gets smaller and smaller the closer you get to the CPU. I'm assuming the entire line, L1 to L3 is 64 bytes. I don't know that to be sure. I don't know if this is like a total, where it's like you add 64 plus 64 plus 64, and that's your cache size, or if it's Like, the total size of a cache line is 64 bytes. I need to look that up. I don't know. But for now, it's safe to assume that it's, like, we know for sure, 100%, it's going to be a multiple of 64, right? So, let's take a look at the diagram again, and let's refactor our function to calculate vector magnitude. So, now we're going to do our first revision, right? Revision 1. Revision 1. Separate code and data into separate code and data make cacheable, right? Calculating the magnitude of a vector is a relatively simple instruction, and the most common case in a game, and definitely in this like little homework assignment we've given for ourselves, is I'm gonna have one function and a bunch of these things. We've already said that they're infinite, but let's refactor our code like this. So let's make this a struct vec2d. And we got f32x and f32y. And so now we can do function, and we can just say it's a static function, and it's vec2d magnitude, right? And so what it's going to take in, actually, no. I've already messed up because we're not returning a single magnitude, right? But what we can do is just say bool, and it'll take in a const int count, const vec 2d in vec2d array, and then we can just say f32 out vec2d magnitude, right? And so there's our function. And so what this looks like is basically, it's going to say, I'm not going to, write the whole thing out, but, just basically for vec, vec less than count or something like that. Let's just use an index. I'm kind of getting ahead of myself here, but we just basically want to do a for loop where we can iterate through that, right? And we're just going to be iterating through each one. So we can just say, come on. Okay, for index, I'm just going to say index less than count, right? And so we're going to basically say, get the current vector, vec current equals like array at the index, right? And we want to calculate the magnitude at that index. So what we're doing is we are iterating through our cache. We are keeping our instructions current, and we're just iterating through the cache. We are going to take hits, but if we were to look at the assembly for our first example, we would see, and Mike Acton did this already in his talk. It's possible C++ has had some more optimization since then, but we can't guarantee that. The point is, the compiler is a tool and it's not a magic wand. We need to hold its hand. Because if you look in that function, every single time it's doing a 32-bit read from main memory. So instead, what we're going to be doing is we're taking that hit up front prior to calling this function, and we are just going to be iterating through it. Simple as that. So every single time the function is called, that's like a mandatory round trip where it's like 200 bytes to read something, 200 bytes to write something. This right here, revision 1. Revision 1 has shaved off multiple orders of magnitude just by doing that. Or at least, it's probably shaved off at least 1 order of magnitude as an average for calculating the same number of vectors, right? So, here's the problem, right? We know that this right here is infinite, and we know that's going to be infinite. But we need to know, what is this, right? What do we make this? We don't know. So, what we need to do, or what we can do rather, we know that we saw from there, we know that our cache size, or our cache line is 64 bytes. Right? So let's do a little bit of math here, a little bit of reasoning. So we know that our out and our, like F32 magnitude we have these 3 values, right? So each one of them are 4 bytes, right? So we got 4 bytes, 4 bytes, and 4 bytes. So that's a total of 12 bytes, right? And the problem is it's not that we are avoiding cache misses, like we said. We want to make the round trip worth it. That also means we want to make sure that our caches are packed completely with, like, every single thing in the cache is packed with data we actually need. Because when we do a cache read, or a cache reload, a read from RAM, let's say if I were loading something, it's going to be filling up that 64-byte cache line with something. And let's say if I only need 1 byte of information, the rest is just noise. It's garbage. But you're doing the work to load it, just to throw it away. So what we want to do is sort of find the balance where we can actually do the math to say, how big do we want this to be? And then we can put that in batches, right? And so 12, I don't think 12 goes into 64. Like, math is not my strong suit. So I did this big post on Reddit where, that I just said, I am not good at math, but I still chug forward. Like, I'm terrible at arithmetic. I'm freaking terrible at it. But don't let that stop you, right? So what we can say is 64, I don't think goes into 12, right? Yeah, it's not a power of 2. So, or rather, but how many times can 4 go into there? 16. We can say divided by... The point is, you can actually calculate, how many of these do you have to put together to actually make sure that you're utilizing the cache line properly, right? So, what if we did this? Let's add another property in here called a scalar, right? Right? And that's another 4 bytes. And that's got us to a power of 2 boundary. So what we can do now is say, how many of these things can I put in here at one time? So 4 of these, or rather, this is going to be right here. One of these is 12 bytes. This one is another 4 bytes, so that gets us to 16. 16 bytes total is needed to calculate one of these things, right? So what that means is we could say something like 64 divided by 12 is... No. 64 divided by 16 would be something like that. So 4. But that's 4 of those, right? And that means that 4 cache lines. If we have 4 cache lines total, that means we can, or rather, I am just getting way ahead of myself. I think that just means, if we do multiples of 4, we will make sure that our cache lines are totally packed with as much information as we possibly need. I think that's what that means. So we can just say, we're gonna always do a minimum of 4 of these at a time, right? So we could do a batch size of, like, I don't know, 32 or 64 or something like that, But we're just gonna say that a batch size is some multiple of 4, right? And I don't know if I'm doing my math right on that. I would, but we can just say batch size equals 4, right? So we're just going to be doing 4 at a time, and a multiple of 4 every single time. We can definitely do more, but, I'm just rambling at this point, right? So, separate code and data and make cacheable. Make into batches, basically. Batch operations. So, remember, we talked about our options, right? And we go back up here. And I am just going to say, like, this diagram is so busy. I am just going to copy this. And go down here. Can I paste? Yes. Okay. Oops. Come on now. All right. So, fuck. I'm just going to be raging at one note, like I said. So, we can use fewer and less expensive instructions. And so, we've already talked about that. Pack, data, and stream processing. Stream processing. And we can batch data, right? This right here, it's not 100% utilization. But if I had to give, like, where does performance live? I would probably have to say 70%. 70% of it is right there, right? Just reasoning about cache utilization gets you in the ballpark. It gets you a passing grade, right? And this is like 70% at a minimum, right? So it just depends on the use case. But separating data into small cacheable arrays, or having a fixed set of data that's processed through a stream of instructions, doing your best to reason about that stuff is gonna get you pretty damn close. But now here comes the scary part to me, is doing things in parallel. Okay? So, and this is gonna be, I guess, the more obvious one, right? Like, what do we do? So, we can do multiple threads. Or, you've heard it, multi-threading. And we also have things called SIMD. with single instruction, multiple data. And SIMD is sort of like a wild card in that it can kind of go between these categories because it's a way of doing the same operation on a vector of data. But for now, like, this is outside the scope of what we're doing today. SIMD is definitely going to be incorporated in It Flies By when we get to sort of like physics processing and collision detection. But it is outside the scope of this. SIMD does not always come into play for everything, right? It just comes down to like, what's the use case? But this is what we're going to be talking about here. And so let's go back to our diagram of a CPU again, okay? I'm going to pull out handy dandy shape tool, and we're going to say, here's our CPU, right? And within the context of what we just saw, remember, we had we saw our physical cores and our logical cores. A CPU has a number of cores on it. So, it has like core 1, I'm just going to say, core 2, core 3. And these are physical dies, right? On the chip. These are physical cores. And a core is basically, it has something called an ALU in it, which stands for Arithmetic Logic Unit. As my professor in college likes to say, it does the maths. It contains all the little traces and circuits for doing all the math that a CPU can do. Arithmetic Logic Unit. And I think it also has an MMC, Memory Management Controller, or something. There's other things that go into a core, but they are distinct physical properties, right? That it's not magic. We like to say that CPUs are rocks that we tricked into thinking, but there are physical things that are going on inside one of these machines. It is a machine. Like, it is just a thing these are things that exist on it, right? And each core, if you have hyperthreading, and you can have something called logical cores. And again, I really hope I'm getting this right. I'm trying to learn all of this. Where a core, I'm just going to say logical core 1, logical core 2, where it's like a physical core virtualizes 2 cores. Right? These right here, these logical units, are the logical processors we are going to be working with. They have actually, I can index them. You can query the operating system for their health. In fact, let me bring up Task Manager really quick. So if I were to go into Performance and I want to open the resource monitor, we see right here that I've got this CPU and yeah, there we go. So here's my 12 cores listed from 0 to 11. 12 cores. There are not 12 physical cores on this machine. There are 6 physical cores on this machine, and each one gives us 2 virtual, aka logical cores to play with. And that also requires us to think of the, I guess, like, anatomy of a program. And so this is where we are getting into, like, what I want to do for It Flies By, right? So let's talk about the difference between a process and a thread, right? So I have my exe, which is a process, right? It is the sandbox that my application at runtime lives in. It is an executable, basically. And a process has at least one thread, right? And so that thread is a unit of execution. So the process is the executable. All the stuff for the program lives inside the process. A process can spawn other processes, but they do not share resources. You have to go through like the operating system and shared memory modes and all this other kind of shit for them to communicate with each other. Named pipes. And a thread is a unit of execution. This is like the minimum stuff that every program has, that when you basically click, hey, I want to launch this executable, or I want to launch this service, or whatever, this is what it's going to have in it going on. But we know that a thread can spawn more threads, right? So we're just going to say this is thread 0, main thread. And thread 1, and a thread can spawn another thread. And so we say spawn thread 2. And so on and so forth, right? We could just keep doing this until we're blue in the face. 1, 2, 3, 4 in thread 5, and for good measure, we can say thread 6. We can just keep doing this. I think Windows can support 64 threads per application, just because it's like you eventually run out of bits in a collection of flags, and I don't know if that's true, but that's essentially how it works. Just for our purposes, we're going to say that's how it works. Now, this whole thing is my program, right? I click on the executable, the operating system starts a process, and I have a thread, the unit of execution, the thing that's actually churning through my instructions on the CPU. And that thread can spawn more threads. And Scott, this is where I'm going to sort of like say, this is where we need to start thinking about the architecture for It Flies By, right? So, similar to memory allocation, a thread is an OS resource, just like memory. Remember, when we make a request to the operating system, we may be switching into kernel mode, which is an expensive operation, and the operating system can just tell us, no, I can't give you a thread right now. The CPU is too busy, things are happening, I'm not going to do it. So, just how we're pulling memory, we want to pull threads, right? The question is, how many? And so this is a note that I'm going to say. Scott Myers did a fantastic talk that was more like an advanced version of Mike Acton's talk on data-oriented design. His talk was on CPU caches and why they matter. And there was a problem where it's like a matrix traversal problem, right? Where I want to traverse a matrix and I want to visit every single node in the matrix, right? So, I have basically, an array of threads, and we're going to say it's n wide. And so I have a, size matrix or something like that. And what I want to do is like count the number of odd numbers in each slot in the matrix, right? So I have a a counter, and so what I do is I say, for each, thread, thread.run, and inside each thread, what it's doing is it's traversing its own section of the matrix. So it's like, I'm gonna say matrix chunk, and it is going to basically, do the is even, right? And it updates the count if it's odd. This is like horrible pseudocode. Watch the talk. He can do it a lot. Dr. Scott Myers, brilliant guy. He's got a haircut that won't quit, but fantastic guy. So, and what happens is over time, we have let's say time, and we have cores, right? Or rather, not cores, but threads. And what they noticed is the time is just all over the place. Why is that? Well, case in point, the first observation, threads are not always the answer. So they're not magic bullet. Threads are not a magic bullet. Just because you throw more threads at a big problem, it doesn't make that problem faster or easier to solve. Because threads are their own unit of execution, and they have to be managed properly. But what's happened is there's something called false sharing. What's that mean? This guy right here was declared outside of the thread of the execution unit. This is on its own separate cache line. Every time one of these threads accesses this, it marks that cache line as dirty, and when it's done, it has to evict it and reload it, every single time, and it basically gets unpredictable, right? So what's the solution? Well, what we do is we keep this global, and what we do is each thread gets its own count. And we just update it locally, and at the end, we just sum counts, right? At the very end. And so what happened there is we had, come on, OneNote. We had perfect scalability. Right? Or rather, I could be doing this wrong. But I think it was something, I don't know if it was time or something else, but rather, we were looking for, how does this scale? If you have more shit, you expect it to, scale linearly, but, scalability is perfect. That doesn't mean it's good, it just means it's predictable, right? As I add more shit, I expect it to, increase or, the amount of things that I could process in a certain amount of time, right? It just becomes predictable. So, we talked about, this is where we've talked about the cache and the cores, right? This is where we need to think about this, right? Because throwing more threads and just declaring shit everywhere, it's not going to solve the problem. And as you have more threads, I can just keep spawning threads all I want, right? I can just spawn more processes and, have, a thing that, a process that runs more threads, a process that runs more threads, and they do different things and, all kinds of weird shit. But that's not what we're going to do, because threads are not a magic bullet. So here's what we're going to do. We're going to have, and we're going to say, engine thread architecture, right? Okay? And so this is what that means. We're going to have one thread per core. We're going to create these threads up front. I'm going to create them up front. And they basically idle until there's work, right? until there's something to do. And each one is going to have its own memory arena. Remember how we talked about memory arenas? Isolated. We're just going to say memory space. We basically are going to be going through the data inside It Flies By, doing like physics calculations, rendering calculations, and all that kind of stuff. And when we're done, we just write everything back. Just like we did, the example in Scott Meyer's talk on CPU caches and threads. So this is what we want to do. And so this is what this is going to look like inside the engine. We're going to have we're going to have a core thread. And so this is, process thread, right? This is the one that the process spawns whenever that the game launches. It is going to be the one that does rendering and synchronizes frame rate. Right? So this is basically the workhorse, like the big wumbo stuff that's going on is it is going to render graphics and audio, and it synchronizes with the frame rate. So it's the heartbeat of the engine, basically, that core thread. And so now what we're going to have, the next thread that we spawn is going to be a dispatcher. So as the game is running and as the core thread is sort of gearing up to do stuff, it's going to have jobs to do. And we don't want to wait on those jobs to finish. We want to add stuff to basically these work tables. And so that's what we have. We have work tables. And these work tables are for different routines, right? We separate things into engine routines. An example of that, of two different routines, would be collision, detection, and collision resolution. Right? So, detecting a collision, if two things have collided, that is a completely separate process and completely different set of data transforms than resolving those things. Because, okay, we've detected that two objects have collided, and the resolution is going to be, okay, did we collide was it like something that was in gravity and it had it was at an angle and it fell down, or was it like a rounded object that collided with a rectangle? It's just different. These are a different set of routines. And so whenever something happens, or we want to get work done, we just say, hey, I'm going to add an entry to this table. And what the dispatcher does is give things to task runners. Right? So process thread, and this will be, T0. And the dispatcher is going to be T1. And so what these do is a routine is divided into tasks, right? So an example would be if we're detecting collisions, it would be, hey, is stuff colliding with the player? Is stuff, raycasting from the camera? Is it colliding with stuff? Basically, they can run small jobs. Read, do transforms, and write back. We keep things isolated like that. And the task runners will do that. And so what these are is our remaining threads. We have T0, T1, and we're going to have T2 to Tn, where n, and this is really important, is number of cores. Or, rather, n minus 1, where n equals number of cores, right? So this one right here is easy. we just say, I am not going to... This is like the main thread, the main unit of execution is just going to be synchronizing the frame rate. Say, okay, engine update and render, and make sure that everything is firing at the frame rate that we've set. The dispatcher is going to be asynchronously taking in task that is defined by the core thread, and the core thread I'm going to also say is the, the game, right? Game logic, okay? So game logic is going to be like, okay, so player input is going to move the player this way and that way, and so what we're doing is we're sending tasks over to the dispatcher, and it will decide which thread is going to run which task. As a concept, that's pretty simple, but implementation is something else entirely. So there's ways that you can do thread pooling like this. I basically want to keep these threads idle for the entire lifetime of the program. So on start, right, create threads up front. We're creating these threads immediately. And so we want them to sit idle, and Windows exposes some methods for us that we don't have to poll. Like, it will basically halt the execution of a thread until a variable gets toggled, right? And they are, it's not critical section, but let me go ahead and pull up the logic here, right? We're finally getting into other things, and I'm trying to wrap this up because it's really heavy-handed. So what we're going to do is say, let's see, are these internal threads? Yeah. So we have a thread, and on creation, what we're doing is we're getting the processor number, and we are manually assigning it to a core, right? So the Windows API says to avoid this, because what Windows will do is it will try to decide which core to run a thread on when it context switches. It's like, okay, I've context switched, and as in, like, it's doing stuff kind of round-robining and doing things all over there's things that are happening all over the operating system, right? The operating system is very busy. But it comes back to our program and it says, okay, what cores do I have available to run threads? And it will basically pick the best core it thinks for the job. That's what the operating system does. But I don't want it to do that. I want it to, the threads to stay locked on the cores that they are spawned on. So what we're doing is up front, and let me go into, let me see, core threads. So this is the function that runs on startup, like inside the game engine. And so what we do is we have a context that we assign to each thread, which is just basically a small pointer for platform-specific stuff, like Win32 thread handles and those kinds of things. We commit some bytes to our program stack, and we iterate through the number of cores we have, and we want to create a thread for every core except the core that is running the main thread. That's it. We basically put an array of these things together, and over here we create the threads, and the routine is just simply a callback, right? It's just going to be calling back to this routine right here, where we pass in the pointer for our thread, the thread that we created on the engine, and what we want to do is just wait. We have a condition variable, which is going to be something that we toggle whenever we say thread awake, right? The thread needs to wake up, and it needs to do its thing. And when it comes back to it, if it falls asleep, it just sits there and waits for work, right? And there's nothing really going on here other than it's just logging stuff, right? And I will go through this more in depth when there's actually things to do that are threaded, but like, this is going on a 2-hour-long video already. So let's go ahead and just show what that looks like at a high level, okay? So I'm going to run this program, right? And if we look here, what's going on is we can see that we are starting up, and we can even see the scheduler, which shows our threads, right? And so core ID 42552. If we go here, I doubt that we'll see that core 552. Yeah. So I don't know why this has a thread ID of 0. Yeah, something weird is going on there. But we are essentially just logging each one of our happy little threads running in its own little execution. And we are not... what we do... I know I've been stuttering a lot. I probably should have made this like a separate video. But here's what we got, right? So we get here where we enter the critical section, and we just wait until something wakes the thread up, right? And so we keep saying task data locked, task data locked. That's when we are just waiting for something to wake the threads up and they can run. And this function right here is just a function pointer and some data that we pass in, which I think will be an arena or some other context that's inside the engine. So what have we done in this short amount of time? We have talked about CPU caches. We've talked about CPU cores and how we can have a thread that runs on each core in a way that doesn't bog the system down. Because if you just keep spawning threads on each core, we're essentially going to thrash our processor. Like, it's going to have way too many context switches, and it's going to get a bit more unpredictable. So, and a little thing about, there's a way to manually assign threads. Like right here, I can basically say, I want to set an affinity mask, and what that is we're telling the thread, hey, there's only a certain number of cores you're allowed to run on. And so what I'm going to do is isolate it and say, each thread is going to run on its own core. Right? So we do the, on startup, how we handle the primary thread is, I'm going to go to Win32 context. And I believe it's somewhere in here. Yes. So what we do is Windows has these handy functions where you can actually get the current thread and processor number that the current execution unit is running on. And what I'm going to do is just set an affinity mask to say, keep it on this core. Right? That's it. When it context switches, it can change. And so what I'm doing is, like in any other context, this would be ill-advised. But what I'm doing is I am going to manually poll each of these CPUs, or each of these processors, and see, I want to assign the task myself, basically, based on the status of each core, right? And that's basically it. Ooh, I've talked a lot. And so, let's talk about revision 2, right? I think we've talked about revision 1. Yep. Rev 2. We've talked about like batch sizes and stuff. But what we can do is parallel process batches on threads. But what we're doing here is we're essentially maximizing the potential of our processor, right? Memory is easy. CPUs are hard. Like, it all comes down to access patterns and how you are working through those in units of execution. I am very tired. There's other really pedantic things that you can do, but essentially, we're just maximizing potential, right? Maximize potential, right? So we have a CPU. We have cache lines. And we have cores. And what we're going to do is just basically this. Don't waste them. Like, what was I talking about with, like, the percentages and stuff? So yeah, our two options here, doing things in parallel, we basically take our batch data, run distinct batches, on separate threads. And this gets you, like, this is like the other 30%. A minimum. And this is like what you can get, right? So it's a balancing. Most of it is going to be in how your access patterns of data. So this one right here. And the other is how you batch and run stuff, right? But if you're going to do this, you have to make sure that things are isolated enough and each thread gets its own cache line. So we want to keep things as separate as possible, right? We don't want to access stuff. If we have like this false sharing thing where two threads are accessing the same pointer, it's not even a matter of like, even if we're just incrementing something, like we don't care about reading it. We're not doing reads after writes or write after write or things like that. We're just constantly updating stuff. But even doing that can thrash the system and make it, make the performance unpredictable. There's still a lot of stuff. We've only scratched the surface, and this is a fucking 2-hour long video, so I think I'm done. I think everybody gets the point right now, but like, this is it. This is it right here. We want to do things in a way that makes access patterns predictable. That's it. And we can do that by querying our processor and reasoning about the data that we have. I'm tired, and I quit. I'll see you all in the next video.